So hello and welcome everyone. My name is Jay Dalsaniya, and in this video we are going to solve the problem merge to BST. So the approach of this question is very interesting, and the idea behind the approach is also very interesting. So pay proper attention, and if you are really enjoyed this videos and this video solutions from Geeks4Geeks, then do hit the like button and share down your approaches and your views on the solutions that this mentor or mentors like me are creating. Okay, so without wasting any further time, let's start the video. So the question says merge two BSTs. You will be given two binary search trees and you are supposed to return the uh, return elements of both BSTs in sorted form. So they will be giving you the root of two BSTs and you are supposed to return the sorted form inside a list of those two BSTs. So let me explain what the question is saying with an example, that is example number 1 given over here. So in the example number 1, two BSTs are given, BST1 and BST2, and you are supposed to merge the nodes of this BST and form a list out of it, and that list should be in sorted form. Okay. So there is one observation that is needed for this question, that is basically if you are having any binary search trees and if you do the in order traversal of any binary search tree in order of BST will always be in increasing order. So this observation is a prerequisite and you should be aware about the observation that in a binary search tree, if you do the in order traversal of any binary search tree, then the arrangement will be in increasing order. Okay, and and you also should be aware about the in order and the traversal techniques of a binary tree or BST. Okay, so what I will do, if I find the content in the in order manner, I'll be getting what? I'll be getting 2, 3, 4, 5, and 6. And here I'll be getting what? I'll be getting 1, 2, I'll be getting 3, 6, and 7. These are the contents of both the BSTs. Now I have a list of the elements, right? Now I can merge this list, and if I merge this list in a sorted form, I will be getting 1, 2, 3, 4. So here we have two appearances of 2. Okay, I have basically two appearances of 2, and then again two appearances of 3, and I'll be having 4 and 6. So I'll be having 4, 6. Okay, so 4, 5, and 6, and we have 6 twice, and then we have 7. So this should be the output, and here it contains the list of elements from BST1, BST2, and it is in sorted manner. So 1, 2, 2. So 1, 2, 2. Then I have 3, 3, 4, 5, 6, 6, and 7. So 1, 2, 2, 3, 3, 4, 5, 6, 6, and 7. So this is the output of the given binary search trees. Okay, so the idea is simple, right? The problem statement is quite simple and straightforward. Merge two BSTs and you will be having a list of the elements, and the elements list should be in sorted form, and you are supposed to return that list. So that's it. I hope you have understood the problem statement by now. Now let's discuss some basic approaches that came to my mind while solving this. Okay, while doing the explaining the question. So approach number 1 that came to my mind is basically find out the in order traversal, right? So that revolves around the in order traversal of the given binary tree. Okay, fine. So as we saw that I can find the in order traversal of BST1 and store it inside a list. Okay. Now I will also analyze the time complexity and space complexity. Now let's say in BST1 there are n elements. In the BST2 there are m number of elements. So this list that I'll be creating will be of size of n and m, right? So extra n and extra m space is occupied, and for storing this entire list I will be needing a larger list. So that list will also be size of what? N plus m. Okay. Now in order to find all the BSTs, it will take order of n time. To find all the BST2, it will take order of m. So the overall time complexity that comes over here is basically order of n plus m, basically to find the in order, to find the in order of BST1, BST2, and then to merge them. Now you should be aware about the algorithm that if you want to merge two sorted arrays without any extra space, then the algorithm that is used inside merge sort can be applied over here. Okay, so that's a prerequisite, that algorithm you should be aware about in order to understand what I am saying right now. So n plus m, I can merge this entire two list in a single list, and that this is what I will be getting. So again n plus m. So overall I can write down order of n plus m will be my time complexity. Now here if I have a look at the space complexity, extra space n, extra space m is utilized apart from this list that will contain our answer. So I can see that the space complexity is what? It is order of n plus m over here in the approach that we are going to use. We are going to use the in-order traversal approach and merge two sorted arrays algorithm. Okay. Now let's see what the question is expecting as our time and space complexity. So here, if I see the expected time complexity, it is saying order of n plus m. Okay, so our time complexity of the approach 1 works perfectly fine. But what about the space complexity? Here it is saying the expected space is height of BST1 plus height of BST2. So this means that we can at max use a recursive in order traversal, because the recursive in order traversal or the in order traversal that we will be following, that will be having the extra space requirement equivalent to the height of the BST. Height of the BST or height of binary tree is what? If there are n number of nodes, that will be order of log n, right? So here it is saying height of BST1 plus height of BST2 plus m plus n, that is for storing the answer. So if we ignore this m plus n, they are saying that the auxiliary space that we expect is order of height of BST1 plus order of height of BST2. But what we got over here as our space complexity is order of n plus m. This is based on total number of elements. Now we need to optimize this thing a little bit. Now in order to optimize this thing, we need to think of a better approach. This approach 1 will not work. As we saw, the time and space complexity are not up to the mark. So this is our time and space for our approach number 1. Now let's analyze the approach number 2. What better things can we do on it? Okay, I hope you got an idea about the approach 1. If you got an idea, that's good, and basically you'll get an idea only after whatever algorithms I have mentioned. If you are already aware about those algorithms, then and only then you will get an idea about how this approach 1 will be implemented and how this order of n plus m will be your time and space. Okay, now approach number 2. So this approach number 2 is also around this in order traversal only. I'm not saying that it will be different or it will be something very different from this in order traversal, but it will be something modified over here. Now what modifications and how we are going to help or take the advantage of in order traversal? So let's see. We already saw that the in order traversal of a BST is what? It is already going, it will already be in increasing order. The in order traversal of a BST will always be in increasing order. We saw this, right? This is our observation that we are aware about. Will always be in increasing order. Now what I will be doing? So here the problem was that I was creating an extra list to store the elements in increasing order, and then I was merging both this list. Then I was using merge to sorted arrays. So here I am saying that don't put all the elements inside this list that you are creating. Don't put all the elements. If you put all the elements, then space will be order of n plus m. Now they are expecting that this space is equivalent to the height of this BST. And we know height of the BST is what? Of any tree that is containing n number of elements, log n. Okay, fine. So now what elements should I insert inside some data or some arrangement so that I can merge those arrangement and I can get the answer list? And that answer list should not be basically in a random order. It should be in such a manner that it is already insorted. So now tell me one thing. We know that the in order traversal, what does in order do? It basically goes to the leftmost node. And what is the leftmost node over here? It is 2. Then it encounters the root node. So it gets to know that this is 3. And it goes to the right subtree. Then it gets to know 4. Now again it goes to the root node 5. And then again the right subtree, it gets to know about 6. Okay, so this is how the in order traversal works. But now tell me one thing. What currently I am saying that this entire BST1 and entire BST2, this is my total number of elements, BST1 elements and BST2 elements. These are the total number of elements from BST1, BST2. Now give me the smallest elements from BST1. Which are the smallest element? Okay, so the smallest element of this BST, I can just fetch the leftmost node over here. So I'll be fetching the leftmost nodes. Okay, I'll just do the in order traversal, but this in order traversal will be a linear traversal. If I pass this 5, it will just move to the left hand side. It will just remove the leftmost, because in the in order traversal we know that it encounters the left subtree, then the root node, and then the right subtree. So I am just focusing, I will extract all the elements in the in order traversal that are of the left subtree and then the root node. Okay, so I will just encounter this many nodes. So what I will do, I will create a stack data structure, and inside this stack data structure, I will insert all the elements that are part of left subtree and their root nodes. Okay, so I can see if this is my entire subtree, I can see 5, 3 and 2. So first of all 5 will be inserted, then I will be inserting what, 3, and then I will be inserting 2. So there is a reason I have taken a stack data structure over here. We know that inside a tree we can only traverse from top to bottom, we cannot traverse in the bottom of approach, but we know that the in order will be in increasing order. So in order starts from the leftmost node, that the last node, right? So I need the last node or the smallest node at the top with me, right? So if I have an arrangement that gives me the smallest node of both of them very quickly, so that would be my stack data structure, and in this order if I traverse the entire BST, both the BST, I'll get the smallest node quickly. So here also I'll do the same thing. As this is my entire tree, I'll go to the root node, and then again I'll go to the left hand side and I'll extract all the leftmost node of this entire tree. So I'll have 2, and then I'll insert 1 inside the stack data structure. So bear with me if you are not able to understand this very quickly, just bear with me. If you are good at in order, pre-order and post-order or the traversal techniques of a BST, then I guarantee you will be able to understand this thing. But have some patience, have a look at what I'm trying to do, what are the next steps and the iterative steps, you will get to know what we should do. Okay, so this was my entire BST over here and over here. Now I have extracted the smallest elements 2, 3 and 5, and here also on the left side, right? So 2 and 1 I have extracted them. Now what I will be doing, I will simultaneously start creating the answer list that will hold my answer. So now tell me, these are the smallest elements from the BST1, BST2. So I can compare the topmost nodes. Again, they are not just the elements. Whatever I have stored inside the stacks, S1 and S2, they are not just these normal elements, the integer value. No, they are actual nodes. Okay, so 2 and 1. Which one is the smallest one? I can see 1 is the smallest one. So what I will do, I will remove this one. Now see, pay proper attention over here. I am removing this one from this because I have placed it inside the answer list. Okay, now what other elements are remaining for this one? So till now what we have inserted the left subtree and the root node. L and D has been inserted inside this stack. Now what will be remaining? The right subtree will be remaining of this one. But do we have any right subtree of 1? Okay, this one is over here, this one. Do we have any right subtree of 1? Not present. So there won't be any impact or no nodes will be included due to this one. If I remove this one, no nodes from the right subtree of it will be included because the right subtree of 1 is empty. Okay, now follow this step again. Okay, so now again check the smallest node, 2 and 2. Which one is the smallest one? I can see both of them are smallest one. So I will go one by one. Okay, so first of all I'll remove this 2 and append it over here. So now let's see the impact. Then I will also come over here. I'll also remove this 2 because they are equal, right? So I'll remove this 2. Now we know that for this 2 also the left subtree and the root node has been encountered. If you don't believe me, then have a look. So left subtree of 2 is this. This is already encountered. Yes or no? 1 was already encountered and it is already there over here. And the root node is also encountered. Yes. So what is remaining? The right subtree is remaining. Okay. So now here from this BST, which elements are remaining? Now only this many elements are remaining. Not entire BST is remaining. Okay. So these are already taken care of. Now I have to find out the same thing, that is the smallest element, that is L and D from this subtree. So what I will do, I will move to this node 3. I will insert it. See, this 2 has been removed, and let me write down a current variable or the current node. So current node is 2. So I will remove the left subtree and the root node. So I will get to know this 3. I'll again move in the left hand side. So I have inserted 3, the node number 3, but the left hand side of 3 is not there. So what I'm doing over here, as I'm saying that I'm removing the left and the right node. So I'll take a current node. Let's say current equals to some root node. Okay, and while my current is not null, I will just keep on adding. Let's say I'm adding inside our stack. So I'll say stack dot push the value of current. I'm inserting the entire node, not only the value, and then I'll move in the right hand side. I'll say current equals to current dot left. I'll keep on moving in the left hand side. So whenever I'm saying I'm removing the left subtree nodes and the root node, this is what I'm doing over. Okay, so whenever the elements are popped from the stack, I only need to encounter the right subtree. So left and the root node are handled when we push the elements inside our stack, okay, and the right subtree will be handled whenever we remove the elements from the stack. So let me highlight this thing as well. So this will help us or handled whenever we push something inside our stack, and the right subtree will be handled whenever we pop the element from the stack. Okay, so now here I have inserted 3. I can see nothing is remaining on the left hand side, so nothing will be inserted further. Okay, so now again you can see 2 and 3, which one is the smaller one? I can see 2 is the smaller one. So what I will do, I'll remove this node 2. And what is the current node? Current node is 2, but it is now the part of BST1, that node, and I will insert this 2 inside my answer as well. Now I have removed. So after remover, what are we handling? We are handling the right subtree of node number 2. For node number 2, do we have any right subtree? Nothing is there, right? So I cannot do anything. Okay, so moving on forward. Now which one is the smallest element? 3 and 3. I can see both of them are smallest one. So let's remove the smallest one from the stack number 2. So I'll remove the node number 3. Okay, and I'll insert it inside the answer list as well. Now we know whenever we pop, we are going to handle the right subtree of the current node. So right subtree of the current node, that is this entire right subtree. Okay, so now we can see that this 3 has already been taken care of. Now what is remaining for this entire BST2? Only this much. Okay, and over here you can see how many elements are remaining. So you have just removed one element from this BST. Again, this many elements are remaining for BST1, and over here this many elements. Okay, so for this right subtree, I'll do the same process, L and D. I will insert it inside my so-called stack data structure. So I'll move to the current, I'll go over here 7, and again I'll move to the left hand side, I'll get to know 6, I'll insert this 6 node, and again I try to move in the left hand side of 6, but nothing is present, so I'll stop the iteration. Okay, so L and D has been inserted inside my stack, okay, for this right subtree. So current node, now its task is completed. Now again find the smallest one, 3 and 6. Which one is the smallest one? 3 is the smallest one. So remove this 3 from the stack. And what is your current node? Current node is 3. Now printed in the output, 3 has been printed. Okay, so whenever we pop, we go to the right subtree of the current node. So what is the right subtree of the current node? I can see 4 is the node that is present over here. Now 3 has been inserted inside the output. So what is remaining? This many elements are remaining. Okay, so right subtree of 3 is what? 4. So here for this right subtree, I will be inserting left and the root node inside my stack data structure. So I'll move over here. This is my root node. So insert 4 inside my stack. Now move in the left hand side, but left hand side is nothing. It is null. So I'll not be able to insert anything. So I have taken care of what? The right subtree of 3. That's it. Now again check the smaller one, 4 and 6. Which one is the smaller one? I can see 4 is the smaller one. So remove this 4. Current node becomes what? Current node becomes 4. So print the data in the answer list. 4 has been printed. Now how many nodes are still remaining from this BST1? So from this BST1 I can see 4 has been printed. Only this many elements are remaining. But now I have to check the right subtree. So whenever I pop any element, I have to check the right subtree of the current node. So current node right subtree is what? It is null. So nothing will be inserted inside my stack. So moving on forward, so 4 has been printed in the output. Again pick the smaller one, 5 and 6. Which is the smaller one? I can see 5 is the smaller one. Okay, so I'll remove this 5 from the stack, and this is my current node. I'll print 5 in the output, the value. Now whenever I remove an element, I have to take the right subtree of this current node. Right subtree of the current node is what? I have 6. So now what is remaining that is not yet inserted inside our stack or has been encountered for BST1? I can see this much part. So what I will do, I'll move on the right subtree of 5, that is over here 6. Now I will keep on moving into the extreme left. I need the smallest element. So left of 6 is what? Null. So nothing will be inserted further. Okay, fine. Now again do the same process. Find the smallest one, 6 and 6. What can I see over here? I can see this 6 and 6 are equal. So I'll remove this 6. Okay, so my current node will become what? It will be now 6. And now the 6 I will be printing in the output. So 6 will be printed in the output. Okay, fine. Now whenever I remove anything from this remove anything from this stack, that is basically after pop, I have to have a look at the right subtree of this current node. What is there in the right subtree? Nothing is present, so nothing will be inserted inside my stack. So what does it mean if nothing is inserted? Now if my stack 1 is empty, it means that everything you have taken care from this entire BST. Now nothing is remaining from this BST1, and absolutely we can see 1 2 3 4 5 6 have been printed, right? So here is 2 3 4 5 and 6, they have been printed from BST1. Now what to do over here? So now you are supposed to just empty the stack number 1 and put all the elements in the output. So stack number 1 contains what? 6. So I'll remove this 6. I'll say current node is what? It is 6 from BST1, BST2. I'll print it in the output. Now again, if you check the right subtree, it is not there. Okay, fine. Now again, remove the node from the stack number 2. 7 is the current node. So print 7 in the output and print 7 over here and print and exits, right? So nothing is remaining from stack number 2 as well. We have printed everything in the output. So I can see all the nodes of BST2 have been encountered and BST1 has been also encountered. And this is our output list. Okay. So in this manner, we are supposed to find out the smallest elements in the targeted subtree. And as soon as we find out the smallest elements in the targeted subtree, compare with the smallest of the BST2. And after getting the smallest element, take one of the node as the current node and explore the right subtree of that current. Okay. So let me just help you with the algorithm, and once more I'll do the dry run if required, but let's go through the algorithm. I'll just write down the algorithm so you can understand it in a better manner. So here, whenever I talked about exploring the left and the root node, I meant this thing. I have to insert this data inside my stack. I'm inserting the root node along with the left hand child, all the left child. So let's write down the name of this function as, let's say, fun or something like that. Okay, so this is for exploration. So I will add it over here somewhere at the bottom, and let's call this as function fun. And you are simply passing the stack reference over here, and you are going to pass the root reference over here. Okay, and let me just remove this brackets. Okay, so this is our function. Now the step number 1, what does our step number 1 say? So step number 1 says basically for the stack 1 and for the BST1 and for BST2. So let's say for BST number 1 and for binary search tree, you are supposed to find out the smallest elements. So what you will do, you will call this function. Okay, and let's imagine the stack for BST1 is what? Let's say step number 0. ST1 is for BST1, and similarly ST2 is for binary search tree number 2. Okay, so I'll call this function. It will help me to find out the smallest L and D from this entire tree. So I'll say ST1 and root number 1. Similarly over here fun ST2 and the root number 2. Now the second step, what will be my second step over here? Let me just put it somewhere else because I am going to write down the entire algorithm below somewhere. Okay, so now second step. So second step is basically we saw how much did we iterate. We iterated until our stack 1 was empty. So until any of the stack is not empty, okay, we will keep on applying the process. When both the stacks are non-empty, you will keep on applying the process. So while I see that ST1 is empty, well, the stack 1 is not empty, and let's say stack number 2 is also not empty. Well, the stack 1 is not empty and stack number 2 is not empty. So what I am going to do in this scenario, we know some elements will be there inside our stack. So what we were doing, we are finding the smallest one. So we check the top of the stack 1, we check the top of the stack number 2. So what I see, if I find that if my stack 1 top, st1 dot, let's say top, the element at the top is basically less than the element at the top of the stack number 2. So inside our answer list, let's say we have created an answer list somewhere over here. Answer list is also there. So these are some prerequisite variables we need to define, right? So what I will do, I will remove the element. Okay, so we know that what we were doing whenever we remove an element, we keep a current node, right? So what I will do, I will say current equals to st1.pop. I'll remove an element and put it inside my current. Now I have to explore the L and D of the right subtree of this current. So here what I will do, I will say I'll call this function for st number 1, stack number 1, and for the right subtree of the current. But before that, I am supposed to add this thing, this current node inside my answer. So I'll add answer dot add current dot data. So what I did over here, I have just added the answer inside my answer list, and then what I'm doing, I'm exploring the right subtree of current, and I'm finding the smallest value over there and inserting inside my stack data structure. Okay, so this is for the element that I find to be smaller one inside st1 and st2. Else if let's say stack number 2 top, stack 2 dot top is basically less than stack 1 dot top. So what I will do, again I will remove the smaller element, current equals to stack2 dot pop. This is a node, okay, and inside the answer I will add this current data. So I'll say current dot data should be inserted inside the answer, and then I'll call the function. Inside the function I will try to populate the smallest element of the right subtree of current. So I'll say current dot write all the smallest. This is the function. The function that I'm calling over here is this function. Don't forget which function I'm calling. This function. Okay. Just explore the left child of current, whatever is the left child. Okay. So that's it. And else part, if we have basically both the elements equal, then I can write down that I will say current one equals to stack1 dot pop. If both the elements top of stack1 and stack2, both of them are equal. Similarly, current2 equals to, let's say, stack2 dot pop. I'll remove the elements. Then again I will do the same thing. I will add this inside my answer dot add current1 dot data, whatever is the data of this node, and inside the answer I will add current2 dot data. Right inside the node current2 dot data. Then again I'll explore the right subtree of current1. So stack1 current1 dot right subtree, and similarly stack2 current2 dot right subtree of it. Okay, so here after removal of any smallest node, you just need to add it inside the answer, and then you explore the right subtree and find the smallest element inside the right subtree. Here same process for every element that I am removing. If I have equal elements, then I am applying the same process at both the end. You can see over here. So that's what I am doing. This is exactly similar to the in-order traversal that we do recursively. And let's say at some instance, any of the stack becomes empty. We saw while we were doing the dry run over here. S1 become empty, right? If S1 becomes or S2, anyone is empty, and at the end, whatever elements are present inside a non-empty stack, you are supposed to add it inside the answer. If S1 is empty and S2 is not empty, then empty this S2 inside the answer. Okay, so that would be our finishing steps. So that would be our point number 3. Let's say if I say while S1 is not empty, then just keep on popping the elements inside the answer dot add the elements S1 dot pop, but this is a node. I will remove the data out of it. Keep on adding the elements. Okay, and here also while S2 dot is empty, I will say answer dot add S2 dot pop. See, in some programming languages, the inbuilt stack function pop basically returns the element, but in C++, I think they don't return the element. So you're supposed to use the peek and store it inside somewhere, some local variables, and then get the data out of it. But in Java, I guess this is going to work. So that's why I'm writing down in this manner. Okay, so pop dot data, and that's it. And at the end, you are supposed to print the answer list, and that's it. So let me just give you this entire algorithm. The algorithm is quite lengthy, but steps are repetitive. So first of all, get the smallest of the root 1 and root 2 subtrees, BSTs, and then while these stacks are not empty, find out the smaller element, explore their right subtree, and insert the elements inside the stack. Okay, so this is the entire algorithm for basically merging two binary search trees. Now let's analyze the time complexity. You might be wondering how is it better than the other approaches. So here, what can you say about this text that I have created? In worst case scenario, how many elements will be inserted inside our stack? So only this function is allowed to insert the elements. And what this function is doing, initially it will make a call. It will be called by this function, by this root. So it will insert 5, 3 and 2. So at any instance, if you look, the size of this S1 will not be greater than the height of the subtree. Okay, so the extra space that you are utilizing over here is equivalent to log n, that is the height of this BST1, plus log m, that is the height of our BST2. So I'll write down height of, this is our BST1 plus height of BST2. So this is the expected approach that has been mentioned inside our question. So here we are not utilizing order of n plus m. Here we are having height of BST1 plus height of BST2 as our space complexity, and the time complexity is order of n plus m. Obviously, you need to iterate over all the elements in order to merge them. Okay, so now I guess we can jump to the coding implementation part. So let's see the implementation part for the same. So this is the function that we are supposed to complete, and the extra function that we need, the function fun, has been mentioned over here. It takes a root element, it adds all the left side elements of this root node. So it takes a current node, while the current is not null, it adds it inside the stack and it goes to the left hand side, only left hand side, extreme left. Okay, so moving back to this merge function, I have taken two stacks S1 and S2. I have taken an answer list to store the answer. Now I'm calling the function for the initial BST1, BST2 and inserting the elements inside S1 and S2. While the stacks are not empty, what I am doing, I am checking whichever is the smallest element. If I see the S1 top is smaller one, then I will insert that inside my temporary element or the temporary variable current, add it inside the answer, and then now adding the smallest values of the right subtree of current inside the stack. So I'll call this function with the right subtree of current and populate the S1. Similarly for S2, and if both the elements are equal, I'll do this for S1 and S2. And at the end, whichever stack is not empty, I will pop all the elements and add that elements inside the answer. And at the end, just simply return the answer. So now let's try to submit this approach and let's basically solve this question. So we can see that the problem has been successfully submitted, and the time complexity of this approach as mentioned, order of n plus m, and the space complexity as observed, height of the BST1 and BST2. And for storing answer, order of n plus m. So that was it for in this video. I hope you really enjoyed the solution of this merge to BSTs. So I would highly recommend that do a dry run on this entire approach at least once. Understand the recursive in-order traversal. After that, you will be able to understand what is happening over here. So that was it for in this video. I will be meeting you in the next video. Till then, keep coding and keep on watching videos from Geeks for Geeks practice problem. Thank you, everyone.